Hello everyone, this is Michael. Today let's look at the linked code number 376. Binary tree parser. In this problem, you're given a binary tree and you need to find all the passes that sum of the nodes in the pass equals to a given number target. A valid pass is from the root node to any of the leaf nodes. So what does it mean? Let's look at this example. This is a tree, and we need to find the target 5. Basically, we need to find all the passes that sums up equals to target 5. Excuse me. So in this tree, we find the two passes. One is 1, 4. The other one is 1, 2, 2. All right. So let's see how to resolve this problem. Thing number one is that this is a tree, so you always think the divide and conquer first. And second one is that actually this is like past searching stuff. So we basically have to perform a search over this tree. And when we do a search, we usually have two ways to do it. One is BFS search, the other one is DFS search. So in this problem, we will use DFS search because every time if you use the DFS search, that's going to be easier for you because you don't have to do any extra stuff. The recursive calls is going to take all the extra stuff for you because when we write recursive solutions, it's always simple and expressive. Yeah, let's see how we resolve this. Directly jump into the code. Binary tree pass sum. This is our entrance. Here we are taking a tree node, and we're taking this target value. So basically, we need to find the all the passes in this tree that all the nodes sums up equals to this target value. And first thing first, we need to do the parameter checking. If this tree, if this root is none, we just return a empty list. And here we define our sum passes, which is our answer we need to calculate. And then we define a DFS function, and this function is obviously a recursive call, and also a DFS strategy search. So after this call is done, all the values will be filled into this sum passes. We just return this self.sum passes. So this is like a template. Then in the second part is which is our core, we'll be focusing on how to resolve this one. But before we do anything, I need to point it out is that during the interviews, it's much better for you to just modulize your code. Do not just put all the code in one function because it's gonna make your code messy and so complicated. It's not easy to read. For the interviewers, they more want to see you have the mindset of modularization. So try to just split the complicated logic into different methods. In our case, the DFS search is really complicated, and a lot of like core logic will be there. So we separate it out is a better approach. All right, so let's look at this DFS search. So whenever you do a DFS search or you do a recursive call, first thing is that you need to give a accurate uh, definition for this DFS search. So what does this guy do? Our definition in this case is this DFS is going to calculate the sum passes that satisfy the target value in a given tree. And we will collect these passes and add them into this global variable sum passes. So that's what this guy do. That's what this guy does. All right. Since this is the recursive call, so we have to do parameter. No, we have to do that condition termination first, because we need to make sure that we can get out of this recursive call, or we'll be having that Stack Overflow issue. So first thing is that if the root is none, definitely we don't have to do any calculations. So we just return, we just do a return. If uh, this is the leaf node, meet and leaf, like this problem mentioned, a valid passes from the root node to any leaf node. So if this is the leaf node, then we just need to perform some calculations. And first things first is that if, because we try to find the target value, we're trying to find the passes in this subtree, which sums up to a target. But right now, if this is a leaf node, so we only have one node, and the target value, obviously, if the target value equals to the root's value, that means okay, cool. We find this condition which satisfies our conditions. Though, so we're gonna just add this value to the passes, and we just put this pass, because this is valid pass. We just put this pass to the our global variable sum passes, and we just return. But before we return, actually one super important thing here is that we have to do a passes.pop. Why is that? Because this passes is a local variable that is used by this DFF search. DFF search is, every time when we go deeper, go down next layer, so the parent actually, or the caller actually, is gonna just pass down the local solutions or local variables to the down layer subcalls. So if we do anything, any changes in our layer about this local variables, we definitely have to recover. If we append something, we have to pop. If we pop something, and we have to append. So basically, you don't want to manipulate this passes in your before you return. You don't want to change anything. You want your color to have exactly the same object. Looks like nothing changed. And in another word is that the DFS search actually is to try all the passes. So we always just try one passes, and we come back and we try the other passes. When we come back, we just have to recover everything, pretend nothing happened before. So this actually is typically called backtracing. In DFS search, backtracing is the most important step. But I see a lot of interviewees, they forgot this backtracing, um, especially in this case, because they think, okay, I'm gonna return, but actually it's not. Just to remember, the rule number one is that if you do a recursive call, if you do a DFS search, anything you changes to the local variables, you got to recover them before you return. All right, so yeah, this is the termination conditions. So if this does not satisfy the termination conditions, that means we have to do some cool logics here. So thing number one is that we always just add ourselves to the passes, local variables. Then we'll be passed down to the next layer. And we always just go left first, go right second. You can just switch, but by convention, we usually just go to left first. Then we just pass our subtree root, and our target value will be the target minus root dot value. Uh, so this is the typical way that how we smaller or reduce the size of the subproblems until we are able to resolve this issue. So this is how recursive call works. We just divide, cut, reduce the size of the subproblems until we can resolve it. Then we just all the way go back to the upper layer colors. In our case is that we just go to the left subtree and we try to resolve these sub problems, and we go to a right subtree, we try to resolve these sub problems, and we all the way passes our passes into the down layer. And same thing here, because in this layer we actually just add ourselves into these passes. So when this layer is done, we just have to do a pop. What does it mean? For example, you have the passes. You go try you try node 2, and you try third layer node 2. Then you realize that okay, cool, this pass works. So we just add this pass to our answer. Then you start to think, okay, cool. Since I tried this too, so I'm gonna just try the other passes. So you before you return to this layer, you have to remove 2 from your local solutions. Then you try to add 3 to see how it to see if it is working or not. And since you tried this left side, you're gonna also you're gonna just all the way back to this layer, and you remove 2, and you go back to this layer, you go try right tree, and you find 4. You can try just add this 4 to the passes. So in the end, actually you have 1 4. So that's how you find 1 4. Actually, it's better for me to draw a pictures to explain this, but I think you can understand what I'm saying. All right. This is the whole algorithm. So let's just summarize it. First thing first is that we have a template. We have something like a template, and we just write the structure or framework of this algorithm, and we put the heavy logic. We encapsulate the heavy logic in a function. We call it the DFS search. Some people they want to call it helper. It's okay, but just remember, before you do anything, you need to give a full definition of this method to let your interviewer know what does this method do. All right, then we put heavy logics implementation here, because the FS search is a recursive call, and we need to do the termination condition testing first to make sure that we can get out of this recursive call. And here we always just add ourselves into the local solutions. Then we go down layer to resolve a smaller issues. And once the current layer is done, since we did some modifications to this local variables, we just remember to backtracing to try some other solutions. This is the overall solutions, and let's just submit and run this algorithm. That's great, it's working. And also here I have some notes. Come on. And the notes actually is also very detailed. If you can understand Chinese, then you can try to get a deeper understanding about this solutions. I can just give some explanations. In this problem, actually, the interviewers just want to test if the candidate has the deep understanding about the DFS search. And in this case, in this problem, actually, we can use the one mindset, which is the downgrade. You can just memorize this downgrade mindset. Actually, it's very simple. Just try to simplify the problems. If in this problem a lot of a lot of constraints or a lot of restrictions, it's very complicated for us to find the solutions. We can try to simplify it first. We can just remove some restrictions. For example, in this case, we have to find the passes that satisfy all the nodes in the pass sums up to the given target. It is kind of really hard. So we just try to why don't we just try to simplify this question by removing this target condition. We just try to calculate all the root to leave passes collections. That is much simpler, right? We do this first, and after this is done, and to satisfy our problem, then we just need to do a filter, right? And sounds like easier. So this is a mindset called downgrade from simple to complicated. Uh, I think is great actually if you can mention this mindset to the interviewer, because the interviewer does not just want you to resolve these questions, resolve these algorithm problems. The interviewer is more want to hear what you think, how your mind is going on. If you have some mindset or methodology, it's gonna just impress your interviewer. All right, second part, let's talk about this DFS search. And DFS search is a recursive call. So this recursive call is gonna just spread over all the nodes in our tree, and for each tree node is gonna perform this function and calculation. And in our case, for each tree node, the DFS search call is always just check if our current local variable, or we call it local solutions, satisfy our conditions. If these local solutions satisfy our conditions, we just add our local solutions. So in Python, we just append this using this way: passes and square brackets and colon. That means like deep clone this list, because this is a reference object is going to be reused by the recursive calls. So when we get our local answers, we don't want this object to be modified by the other layers of the recursive call. So we just deep clone and add it to our global solutions. And also you can just imagine the DFS as a full search all over the tree. It's like a virus spread over each tree node, and each node is going to be infected and calculate or perform the DFS options. Um, Here is one thing you need to mention is that in each node, or each calculation node, we always just compare the global solutions. And in some cases, actually, in a lot of cases, in the DFS search, in the DFS search logic, we usually just compare the conditions with some global variables, so that each DFS search call is able to see some global variables. We're not exactly using that way, but you can just have this thing in your mind. And we can also just mention another algorithm, or mindset, which is the divide and conquer. And divide and conquer usually just focus on the current layer of solutions. So usually you don't reference the global variables in the divide and conquer, but in DFS search, actually, usually we just set up some global variables by using this self dot stuff, and so that each DFS subcall can see the global variables and can perform some things. We also give a names for that, which is called traverse. In the future, we will be covering more and more about that. All right. I think that's it. That's today's algorithm. And thanks for watching. And Thanksgiving is coming. And happy holidays. Goodbye.